Okay, in this video I want to try and convince you that the dimension of a vector space matters. We're going to be looking at this particular theorem that says you can show that a set is a basis by showing either that it spans this vector space, that it's linearly independent, or that the number of vectors is the same as the dimension of E. And if you show any two out of those three, you get the third one for free. If you think back to the original definition of a basis, it's actually just the top two. But then if you know the top two, you know that that number of vectors has to also be the dimension of V. We had a similar theorem when we were looking at bases of Rn, which was in section 1.5, but we're going to come back to it talking about any old vector space. Okay, so the first example I'm going to look at is the set S is x squared plus 1 and x minus 1, so two particular polynomials in P2, which is a set of polynomials of degree less than or equal to 2. If I want to know if this is linearly independent or not, if I want to know if this is a basis or not, I have to show these three things. And probably checking the dimension is the easiest of those three, by far. Just count the number of things. We definitely have two vectors in S, and P2, if I wanted to find a basis for P2, my basis for P2, everything that's a polynomial of degree less than or equal to 2 would be a linear combination of 1x and x squared, because it would be an ax squared plus a bx plus a c. So it's up to you if you want to call the basis 1x and x squared or x squared, x, and 1. And later on we will talk about ways in which the order of the basis matters. So we might consider these two different bases, but notice that they both have the same number of vectors, which is 3. So if a basis has 3 vectors, that means the dimension of P2, or dimension of V, is equal to 3, but this only has 2 vectors. And so that's enough right away to say it's going to fill the third condition. The number of vectors is not dimension of V. So I can say right away S is not a basis of P2. And I can actually go a little bit further. I can say which of the two parts of the definition does it fail? Does it fail to span, or does it fail to be linearly independent? Well, it should be pretty obvious which one that is, because a set of two vectors can only be linearly dependent if they're multiples of each other, which these are not. So it's probably failing to span. And you want to think about spanning as being there's enough vectors. And if we only have 2 and we're supposed to get 3, we don't have enough. And so I could also say that S does not span. Okay. So let's look at another example. Consider S is the set of a bunch of random matrices in the vector space M22, which is the set of all, or the vector space of all 2 by 2 matrices. And if you look at S, it has 1, 2, 3, 4, 5 vectors in it. So let's see if we can compare that number of vectors to the number of vectors in a basis of M22. So M22 would be the set of all things that look like A, B, C, D. And so a good choice of a basis, if we split up the A's, the B's, the C's, and the D's, a good choice of basis would be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, and 0, 0, 0, 1. And if you run through and check all the details, this set should be linearly independent. It should span the set M22 pretty obviously. If you take A times this, B times this, C times this, D times this, you'll get any possible matrix. And so the dimension of M22, which is the number of vectors in a basis, well, here's a basis that has 4 vectors in it. So the dimension of M22 is 4. S has 5 vectors. And so right away I can say S is not a basis. Okay, and so let's think about what's the problem. Which one is it failing? The two parts of the definition of a basis are it spans and it's linearly independent. And we have 5 vectors in a 4-dimensional vector space. So that's like if I told you I had 3 vectors in 2D, well, you would know that there's some kind of dependence among them. They can't be 3 different directions that don't have anything to do with each other, aren't a combination of each other. And we have the same problem here. We have 5 vectors and only a 4-dimensional space, so they must be somehow depending on each other, or there must be some relationship among them. Okay, so basically, moral of the story is if you don't have enough vectors, then you're not going to span the vector space. If you have too many vectors, you're not going to be linearly independent. The sweet spot is the basis. It has to have just the right number of vectors, and then if you can show either one of these two, spanning or being independent, that's good enough to say that it's going to be a basis.